Hello everyone, I'm Charmaine Cordova, and today we will tackle about the Nilpotent group, which is one of the topic in Abstract Algebra 2. We will also find out some Nilpotent theorems and two mathematical personalities at the end. Let's get started. Let's start from the first theorem, Theorem 8.2.12. Let G sub I, where I is equals to 1, 2, and so on and so forth to n, be a nilpotent group. Then G sub 1 cross G sub 2 cross and so on and so forth, G sub n is nilpotent. Proof. The desired result follows by lemma 8.2.11 and induction. The following theorems give several equivalent conditions of a finite group to be a nilpotent group. In particular, the following theorem describes all finite nilpotent groups in terms of p-groups. It is an analog of the primary decomposition theorem for finite abelian groups. In Theorem 8.2.13, let G be a finite group, then the following conditions are equivalent. The first condition, G is nilpotent. The second condition is, if H is a proper subgroup of G, then H is a proper subset of n sub G of H. The third condition is, every maximal subgroup of G is a normal subgroup of G. The fourth condition is, every Salo subgroup of G is a normal subgroup of G. And the fifth condition, G is isomorphic to a direct product of P groups. Proof. The first condition implies the second conditions or follows the second condition. Since G is nilpotent, G has a central series. Let the set E is equals to G sub 0, subset of G sub 1, subset of G sub 2, subset of so on and so forth to subset to G sub n equals to G. Now, G sub 0 is a subset of H, and H is a proper subset of G is equals to G sub n. Hence, we can find an integer m greater than or equal to 0 such that G sub m is a subset of H. But G sub m plus 1 is not a subset of H. Thus, there exists a element of G sub m plus 1 such that A is not an element of H. Now A of G sub m is an element of C of G divides G sub m. Therefore, for all H element of H, AG sub m times H of G sub m is equals to H of G sub m times AG sub m. This implies that H inverse A inverse HA is equals to AH inverse HA, which is an element of G m subset of H. Hence, A inverse HA is an element of H, and so A inverse HA is a subset of H. Similarly, EHA inverse is a subset of H. Thus, H is equals to A inverse times AHA inverse. A is a subset of A inverse HA, subset of H, and so A inverse HA is equals to H. Hence, A is an element of n of H. Consequently, H is not equal to n of H. Second condition follows the third condition. Let H be a maximal subgroup of G, then H is a proper subset of n of H, and n of H is a subset of G. Since H is maximal, n of H is equals to G. Thus, H is normal. The third condition follows the fourth condition. Let P be a Salo P subgroup of G, such that P is not normal. Since G is finite, there exists a maximal subgroup H of G such that n of P is a subset of H. By the third condition, H is a normal subgroup of G, and let A element of G. Then AP A inverse is a subset of AN of P. A inverse subset of AHA inverse is equals to H. Hence, P and APA inverse are Salo P subgroups of H. Thus, there exists H element of H such that H of APA inverse, H inverse is equals to P. Therefore, HA is an element of N of P, and N of N of P is a subset of H. This implies that A is equals to H inverse HA element of H. Hence, G is equals to H, a contradiction. Thus, P is a normal subgroup of G. The fourth condition follows the fifth condition. By workout exercise 7 in page 208, G is a direct product of its Sylo P groups. Since every Sylo P group is a P group, G is a direct product of P groups. The next one, the fifth condition follows or implies the first condition. The result here follows by theorems 8.2.4 and 8.2.12. We conclude this section by showing that the converse of Lagrange theorem holds for finite nilpotent groups. In theorem 8.2.14, let G be a nilpotent group of order M. If n is greater than 0 and n divides M, then G contains a subgroup of order n. Proof: if M is equals to 1, then the result is trivially true. Suppose M is greater than 1. There exists distinct prime integers p sub 1, p sub 2, and so on and so forth, p sub k, such that M is equals to p sub 1 to the power of r sub 1, p sub 2 to the power of r sub 2, and so on and so forth, p sub k to the power of r sub k, where r sub 1 or r sub I rather are positive integers. Let h sub I be the Sylo P subgroup for P is equals to P sub I, where I is equals to 1, 2, and so on and so forth to K in G. Thus, by theorem 8.2.13 and workout exercise 7 in page 208, G is equals to H sub 1 cross H sub 2 cross and so on and so forth to H sub K. Since n divides M, there exist integers t sub 1, t sub 2, so on and so forth to t sub k, such that n is equals to p sub 1 to the power of t sub 1, p sub 2 to the power of t sub 2, so on and so forth, p sub k to the power of t sub k. Now, the cardinality of h sub I is equals to p sub I to the power of r sub I, and so by the theorem 7.3.1, each sub I contains a subgroup A sub I of order P sub I to the power of T sub I for I is equals to 1, 2, and so on and so forth to K. Thus, B is equals to A sub 1 cross A sub 2 cross and so on and so forth cross A sub K is a subgroup of G of order N. Now let's move on to workout exercises so that we can understand nilpotent groups more clearly. In exercise 1, find a central series G sub 0, subset of G sub 1, subset of so on and so forth, subset of G sub n in D sub 4 such that G sub 0 is equals to the set E and G sub n is equals to D sub 4. The composition of A is equals to 4, the composition of B is equals to 2, and BA is equal to A cube B. Now, the set E is equals to G sub 0, subset of G sub 1 is equals to the set E and A squared, subset of G sub 2 is equals to the set E A squared A cube, subset of G sub n is equals to D sub 4. Is a normal series in D sub 4 since the cardinality of D4 divides G sub 1 is equals to 4 and the cardinality of D sub 4 divides G sub 2 is equals to 2, it follows that D sub 4 divides G sub 1 and D sub 4 divides G sub 2 are commutative group. Thus, G sub 2 divides G sub 1 is a subset of D sub 4 divides G sub 1 is equals to C of D sub 4 divides G sub 1, and D sub 4 divides G sub 2 is a subset of C of D sub 4 divides G sub 2 is equals to D sub 4 divides G sub 2. Since Z of D sub 4 is equals to the set E and A squared equals to G sub 1, it follows that G sub 1 divides G sub 0 is a subset of C of D sub 4 divides G sub 0. Hence, the set E is a subset of the set E and A squared, subset of A squared and A cubed, subset of D4 is a central series. Exercise 2. Give an example of a group G such that G is not nilpotent, but G contains a normal subgroup H such that H and G divides H are nilpotent. Solution. The symmetric group S sub 3 is not nilpotent. Now A sub 3 is a normal subgroup. Since the cardinality of A sub 3 is equals to 3, A sub 3 is commutative and hence nilpotent. Also, the cardinality of S sub 3 divides A sub 3 is equals to 2. Thus, A sub 3 divides A sub 3 is commutative and so is nilpotent. Now we already finished knowing some of the nilpotent theorems. Now let's move on knowing the two mathematicians' personalities which contributes a lot in mathematics. The first one, Camille Jordan. He was born on January 5, 1838 in Lyons, France, into a well-to-do family. At the age of 17, he entered the École Polytechnique to become an engineer. During his time as an engineer, he had an ample opportunity to carry out his mathematical research and to write most of his 120 papers. He retired as an engineer in 1885, and from 1873 until 1912, he taught at the École Polytechnique and the Collège de France. So Jordan was a universal mathematician. He published papers in all branches of mathematics of his time. In analysis, he originated the concept of a bounded function. In topology, he showed that a plane can be decomposed into two regions by a simple closed curve. Primarily, Jordan was an algebraist. He became famous at the age of 30, and for the next 40 years, he was considered the master of group theory. He was the first to develop the theory of finite groups and its application in the direction of Galois. He originated the concept of composition series and proved that the first half of the famous Jordan-Holder theorem. More than that, he studied solvable groups in a very general sense. In 1870, he collected all his results on permutation groups for the previous 10 years in Traité des substitution. And his Traité des substitution became a Bible in all areas of group theory. Jordan's deepest result in algebra were his finiteness theorems. He was joined by Felix Klein and Sopos-Lie in the study of groups of movements in three-dimensional space. And his course De Analyse, published in the early 1880s, had a great influence on mathematics and set the standards for rigor. In this book, he showed how multiple integrals can be evaluated by successive integrations. And in his studies of solvable groups, he made extensive use of concepts such as normal subgroup, homomorphic images of a group, and quotient groups. He was the first to use the term simple group, but unfortunately he died on January 22, 1921. So that's the life of Camille Jordan. The next personality is Otto Ludwig Holder, and he was born on December 22, 1859 in Stuttgart, Germany. His father was a professor of French. He received his early education in Stuttgart. On a colleague's suggestion, his father sent him to Berlin in 1877. At that time, Weierstrass, Kronecker, and Kommer were teaching there. In his dissertation, presented in 1882, Holder developed a continuity condition for volume density that bears his name. He gave the first complete general proof of Weierstrass' theorem and also examined the convergence of the Fourier series of a function, which was not assumed to be either continuous or bounded. After receiving his doctorate, Holder attended Kronecker's and Klein's seminar and became interested in group theory. He completed the proof of the so-called Jordan-Holder theorem on composition series by showing the uniqueness of the factor group, which is now a fundamental concept in group theory. He also studied simple groups. Other than the known simple groups of order 60 and 168, he showed that there is no other simple group of composite order less than 200. He also investigated the structure of groups of orders p cubed, pq squared, pqr, p to the fourth power, and n, where pqr are primes and n is a square free integer. He also worked on geometry and number theory, but Holder died on August 29, 1937. That's all for my report for today. We have tackled some nilpotent theorems, and also we have we have talked about two mathematician personalities, which also contributes a lot about our topic and also to other areas of mathematics. And if ever you have questions, you can also freely ask in private. So that's all for today. Thank you for listening and watching with me.